really long for this last part, which I'm sure your brain will appreciate. So there's a lot of stuff we could talk about with firing. We could do this for a couple of weeks, but we're going to hit the high spots. And so what's our goal in firing? Well, we've now got a dry brick. Hopefully it's fairly defect-free, got good dimensions. Now we need to develop the bond that sticks it together. Okay, so the point of firing is there's some sort of ceramics where we use glass as the bond, and that's what we do. We call that vitrification or a vitreous bond. It's an old word for glass. There are other types where it's like some of the electronic ceramics that might be in your phone are more of a solid state. There's no glass involved. It's just you make the materials densify with themselves with temperature. But we're going to use temperature to create this glass that glues the product together. So as we're making the glass, it's spreading out over the bigger particles, and because of surface tension it pulls those particles together where we get fire shrinkage. So the extent of that glassy bond is going to determine our strength, to some extent determine our shrinkage, and the glass also helps us with sealing up pores. Okay, so the reason we had Mike go first is that's our target, and now we're going to talk about how we get to that target. So in a traditional ceramic, I like to think of it as we got a glassy glue in the brick holding it together. So we're making the glass and we're trying to spread it out uniformly over those bigger particles, and that's what gives us our strength. Some technical ceramics, like I talked about, some use what we call liquid phase centering, some use solid state centering. We don't really need to know that much about it, but there are different types of heat work that you do in the kiln. And it is that. Remember we talked earlier about temperature and time? The best way to describe what we do in the kiln is heat work. Okay? It's not just a function of the firing temperature. It's a function of the firing temperature and the time that it was at that temperature. So it's a combination of the two that give us our properties. So yeah, like we said, some systems go into the solid state state centering. So this is a diagram. It's kind of an interesting diagram, but it shows us what all happens with the materials in the body. So if we take a very common brick, we've got quartz, and we've got a certain amount of quartz that is going to hopefully be reduced somewhat. So this is SiO2 in the form of a quartz mineral, and some of that quartz we hope is going to get incorporated into our glass. Okay, we theoretically like to come out with less quartz than we started, but on cooling it's still going to go through this beta to alpha transformation. And it's possible if we get it hot enough, and most brick this isn't going to happen, but some of that quartz is going to convert to cristobalite. Okay, and that cristobalite is going to be left over, just like we talked about. Remember we talked about inversion and conversion. So this would be a conversion of some of that starting quartz into cristobalite. They're both SiO2, just different organization.
I thought we didn't get hot enough to create cristobalite.
If you did, that's what would happen. It's in your deck block. Those do get hot enough, but not in our brick. I've seen it once or twice in some special cases, but it's not common. So then we're left with the kaolin, the chlorite, the illite, or the mica. All are somewhat similar in composition. Some of those are going to get converted into glass. Some of them are going to react to form this compound mullite. Mullite looks, if you can see it in the glass, it looks like little needles, okay, floating around. And it typically helps with the strength. It's usually a good thing. So they're pushed the wrong button. They're different materials that we see in the final product. So we're trying to make as much glass as we can without deforming the body. And so things like the feldspar, this is another type of feldspar material. These guys have a lot of flux usually. See, it says sodium rich. Those go into promoting that glassy phase. And these are, if you've got calcium, sometimes you'll see will last the night in the fired product. So what we do is we can look at the chemical analysis, and that chemical analysis tells us the pieces, like I told you. And then we can also, in the fired product, and we'll talk a little bit about how we measure all this, we can do something called X-ray diffraction, and it tells us what pieces are left over. So one of the things we're looking for too is we may start out with some sort of iron in the material. It could be an oxide, like red iron oxide. It could be iron hydroxide. There's a phase I have trouble pronouncing called goethite. It's iron hydroxide. There's siderite, iron carbonate. But those things tend to convert over. Either this is red iron oxide, think hemoglobin, blood, red, okay. This is Fe2O3. But when we flash, or if we're doing a reducing firing, all we do is we change the ratio of iron to oxygen here, and we can go from a red iron oxide to a black iron oxide. The magnetite, or the black iron oxide, is actually a little bit magnetic. We've made magnetic brick before with the high iron contents. But all it's doing is playing with the ratio of the oxygen to iron. And that's what this is. So you see, this is a bloated brick. Okay, that's a cross section. You see this mess left here. Is that carbon? It's what's left over. So what happens when I get, there may be a little carbon in here, but that's mostly the iron you're seeing. When I get it hot enough, if there's carbon still left around, you get to a point where the iron, or the carbon, wants the oxygen more than the carbon, okay? And it will steal it away. And so you make carbon dioxide gas, which, depending on how permeable the outside is, can get trapped and cause the bloating. And so we've converted our red iron oxide, the Fe2O3, into the black iron oxide, Fe3O4. And you can have intermediates in there. And that's how you get that color range when you flash, okay? So you can go from the blue blacks to the more red blacks and all kinds of colors in between. But all you're doing is manipulating the ratio of oxygen to iron in that case. This case, the iron gave up its oxygen, some of its oxygen, to get rid of whatever carbon was left. So that goes on in the body. You've got organic material that theoretically burns off. So very interesting diagram, a lot of stuff going on. But basically your goal is you're trying to make this glass. These things that are sodium or potassium rich help in creating that glass. And that glass is going to stick together the bigger particles that are left over after everything happens. So,
is that glass like what, the Windows kind of glass?
It's a silicate glass, which is like what's in Windows. What's in Windows is pure, so you can see through it. This is more,
So that's
you know,
content turning into that?
some of it is. Some of that, remember the sodium and potassium we talked about, is helping some of that convert. And some of the leftover clay mineral is going into that glass. So a lot of things are going in to form that glassy material.
Okay.
Okay? So the glass can be sort of a trash can, if you will. It can take a lot of different stuff and hide it there. We've been, and by we I mean I've been working with Jim and Garth and some people trying to figure out metals emissions that may take place in the kiln for the HAP. And what happens, the EPA method, this is a little aside, but when it's in the clay material, you're basically trying to dissolve the metals out of it. And we're talking parts per million levels. If we're talking about mercury, it's parts per billion. So we're trying to dissolve that material out and get it out for analysis. Works great in the dry material. Once we've made this glass, most of those metals have been incorporated into the glass and they're no longer available for anything. So when we try to run the EPA test, we can't get it back out of the glass, and it looks like we've had a really high emission, although if we do other techniques, we can see it's still there. So very interesting, all the stuff that goes into the glass. People have even tried ideas where they take nuclear waste and they make glass cylinders out of it. And it can be very stable for a long time for safe disposal. So glass is kind of a magic thing for us, and it's what gives us our strength, and lowers our absorption. So we've already seen this graph in the same day, so I won't go over it. But basically, remember, these are the sort of the backbones of the clay mineral. Usually the higher number tells us more alumina. But when we're talking about firing, we're interested most of the time in these guys. The sodium and potassium are our fluxes, and they promote the glass phase. Then the iron oxide we talked about helps us with the color of the body. And it could be manganese. But basically, if you looked at the periodic table, that stuff right there around iron is what gives us all our colors. Okay, so if you're making a glaze and you want to give it a particular color, you'd figure out which element gave that color, and you could design your glaze that way. Like blue, you use cobalt. Okay, greens, nickel. Sometimes it can be copper. Copper can make a whole bunch of colors. So there are different elements that you would incorporate into the glass to get the color you're interested in. But for our types of materials, most things are iron, manganese, and occasionally you see chrome come into the picture. So if we look at what of mixtures, heating mixtures of alumina and silica, because remember in this slide I showed you those are the majority elements in all of these. That's most of the stuff that's there, with iron being the next most prevalent usually. If we had a pure mixture of alumina and silica, and we added a little bit of sodium, we'd see our first glass phase somewhere around 1400 Fahrenheit, where this mixture would be above 2,000 degrees Fahrenheit, well above 2,000 degrees Fahrenheit. Potassium is also a very good flux. It just tends to be a little more expensive, the compounds you get it from. Calcium can be a little bit of a flux. It can be a little difficult to work with. Manganese, not so much, but iron oxide can even be a flux. So when we flash, we'll talk about it a little bit tomorrow, we're actually promoting glass formation. Okay, you get more glass formation at a particular temperature when we're firing in a reducing atmosphere. And part of that explanation sometimes is normally we're dealing with Fe2O3. This is FeO, so this is a lower ratio of oxygen to iron. This acts a little bit like a flux, just like the sodium or potassium. So we have a number of tools that we use when we're looking at firing behavior. And we do this kind of stuff all the time. You have the capability here to do some of this, but we use TG, thermogravimetry, scanning, differential scanning calorimeter, sometimes known as DTA. This tells us where reactions happen. So when we talk about the clay mineral decomposing or calcite decomposing, this is what we use to look at it. Differential scanning calorimetry, or DTA, tells us heat changes. So if we want to see where the quartz inversion happens, or how big the peak is for the quartz inversion, we would use something like this. When somebody's originally setting up a kill schedule for your raw material, they probably did dilatometry. And basically you're firing the material and you're looking at where it starts to shrink and vitrify, okay, where you're starting to get the glass formation. And then, we have a special instrument where we can look at the gases that come off. So we can see the water, the SO2, and we can do some other analysis for problem materials when it comes up. So just to briefly go through what the instruments look like, I won't spend a long time, and then we'll look at what some of the data does and what the data tells us. So this is that TG. So basically this is a balance down here. We have a furnace on the top. The furnace slides down over the sample, and you're talking a small sample. You always do that in the lab, which makes it a little difficult to interpret results because you've got excellent airflow in here, small sample, good heat contact. So the temperatures we typically predict off of lab equipment are much lower than what you actually see in the plant, just because it's a smaller operation. more uniform temperature distribution, better atmosphere control, things like that. So we can study a number of things that go on in the raw material, and I'll show you some examples. If we want to measure that heat flow, this is called a DSC, and I won't spend too long on it, but basically if I look top down, I've got 2 cups, okay? And the way to think about this thing working is you've got 2 separate heaters that are trying to keep the 2 samples at the same temperature, okay? So if this is my sample and this is a reference that's inert, and my sample has carbon in it, and the carbon starts to burn, it's going to get hotter than the reference. So that means this heater has to work harder to keep up, okay, to keep the 2 at the same temperature. I can measure how much energy, that extra energy that heater took, and I can calculate from that how much energy was released by the carbon burning, okay, is basically how that works. Or when the clay mineral decomposes, it's what we call endothermic. When it gives off heat, we call it exothermic. So when the clay mineral starts to decompose, this guy starts to get colder. And so this heater has to kick in to supply extra heat to keep the 2 together. And I can quantify how much energy is consumed by that reaction. So it's useful. We use it like I teach a burner and combustion class. I just finished one, thank goodness, this last semester. And we can use that to calculate how much energy input. If you know the tonnage going into the kiln and you analyze the raw material and you know what all the reactions that have to take place, you can calculate how much fuel you need to burn theoretically to fire the body. And we use this kind of analysis for that. So we just finished that. Also, we can use it to measure quartz if we need to for an MSDS sheet or something like that. That's one of the ways. This is actually, there's another way we mostly do called X-ray diffraction. But if the amount's too small, this is actually more sensitive, and we can do very low-level measurements there. This is the dilatometer, so basically that little red thing is the sample. There's a push rod that connects it to a measuring device that's over here. Furnace slides over. We can control temperature and atmosphere, and we'll look at some curves from all of this. Only problem is it's a very small sample. So if you've got big features, big grains in the sample, sometimes you're approaching the size of those grains, and you may have to run a lot of different measurements. But this is used on fired brick for architects to figure out the thermal expansion coefficient, so they know where to place the expansion joints in the building. The quartz inversion we've talked about. We've already seen some diagrams that came off this, and then it'll tell us where that glass formation starts and where shrinkage starts. Evolved gas. Really, we don't need all the details, but this can help us to understand emissions and things. We've done a lot of work over the years trying to understand where fluorine emissions come from, or chlorine, the stuff you've got your scrubber for, trying to understand that kind of stuff. So the way this is typically used to develop a kill profile is first you look at all the reactions that have to take place. If you're trying to size burners, you may look at the energy that's involved in each step. So there's energy that goes into just heating the product, and then there's extra energy you have to supply for reactions, like when the clay mineral breaks down. So most of those reactions, we can predict the temperature from this instrument, but since we're dealing with a kinetically controlled process, we usually predict a lower temperature than what you see in the plant. And that's some of the interpretation that has to take place. So we have to keep in mind that firing is a function of not only temperature, but time and really atmosphere. Okay, because I can influence color by change of a high iron body by manipulating the atmosphere. You do that when you flash. So it's a very complicated relationship. Carbon burnout, again, is a function of temperature, time, and how available oxygen is in the proper section of the kiln. So if there's no oxygen, you're not burning the carbon. So it's dependent on all three. So the basic reactions we see in our material, this is a fancy word, but it's just a breakdown of the clay mineral. Okay, so this is where that clay mineral stops being clay and becomes something else. It gives off its chemical water, and we can see that water coming out. They used to call it in old beehive kills water smoking. I've heard the term, where you would see a plume, and it was basically steam coming out from the water that's coming out of the clay mineral. We can see that in some of these measurements that I'm going to show you in just a minute. If it's a kaolinitic material that we're starting with, we're going to get to a point where we start to crystallize mullite. Okay, so you start to make those little needles that help to reinforce the body, and traditionally that's thought of as a good thing because it helps with strength if you've got a lot of mullite in the body and you do a good job of forming that. And then we can see where we start to get our glassy phase that we're trying to make to glue everything together. So this complicated looking thing is what happens when I heat up kaolin. And basically those reactions we're telling you about, this blue line is showing you the heat curve. So the green is the weight curve, and then this dark blue is water vapor. So I can heat to a point where it starts to lose weight. That's where the clay mineral's decomposing. I get a big spike in water coming off of it because that's the clay mineral breaking down. And I have an endotherm here that I can actually figure out how many BTUs per pound that's consuming in that particular step if I wanted to. So as we come along here, one of the things you learn to look at is the way this thing slopes. It's telling me that it's either shrinking or we're starting to get some glass phase because it's pulling away from the crucible wall. Just something you learn, but you're probably getting some glass out here. This isn't the most pure kaolin, but this is that mullite formation. It happens spontaneously, and it actually gives off a large amount of heat. You would normally think of an exotherm being up, giving off heat, but this is German equipment, and their convention says that an exotherm is a downward facing thing. We can switch it, but that's the software always defaults back to this. So we can measure how much energy is given off in this. We've had cases using this kind of work where we had somebody change from using the brown manganese, Fe3O4, which has basically been heat treated so that it's given off all its oxygen, to MnO2, and they were making solids. And the first car that made it to the hot zone, the temperature fell, and they couldn't recover temperature. Couldn't figure out why. Well, we started looking at it, and the the Mn3O4, the brown manganese, it's very flat when we heat it. It doesn't have any endotherms. The black manganese goes through several steps where it gives off oxygen, which can be beneficial, but basically they couldn't overcome the amount of energy that manganese was consuming just by changing the form of the manganese. And of course their brick came out too big, water absorption too high, and they were not happy until we explained it to them. So this is a typical shale. The only thing different here, this red line, this is showing carbon dioxide coming off. So this is showing a carbon burnout. So this has a fairly low temperature carbon burnout. It's happening, this would be, your early preheat, 400 to say 1,000. In reality, you'd probably see it shifted by 100, 200 degrees where the peak is. But again, in this operation, we've got really good airflow. We've got 20% oxygen, so there's plenty of air for this to take place. What I always find kind of interesting, though, is the carbon emissions typically really slow down once this is the clay mineral breaking down, this blue. And I've always thought about that as that's the steam pressure is pushing the oxygen away, and it can't get to the carbon during that period. So when that dehydroxylation takes place, usually carbon burnout stops. This higher temperature carbon, it could be leftover carbon, but in that temperature range, usually you suspect that's a little bit of limestone. You can pick that out from these types of analysis. So this is a series of dilatometer curves, and what we were doing with this, Mike will talk about a variant But basically, we're heating to different temperatures to measure how shrinkage is influenced by the firing temperature we're going to. So we go to 1922, we get a little more than 1% shrinkage. If we go to 2057, we're getting a more than 3, and 2120, we're getting more than 3.5. What we were looking at here was how much this quartz changed if we were consuming more of the quartz, and we really didn't see that. The magnitude of that change from the quartz inversion on cooling wasn't as big as we expected it to be. So there's a series of articles on our website Dr. Brosnan wrote called A Primer on Firing. And basically, you know, your curve may have a few bumps or it may slow down in periods, but basically you got a preheat and you got a soak and then you have a cooling, okay? And we're talking in this area what typically happens. So you've got your carbon burnout in the first part of that preheat, followed by your dehydroxylation and your quartz inversion happen fairly close together. And any residual water in the body, yes sir?
So on the preheat, on our profile it shows that the temperature goes up, it drops back down by 100 degrees right around, I think it hits like 700 and then it comes back down to 6, goes up to 900. So is that it? That
could be to allow more time for carbon to burn out. I'm not sure why,
Okay.
but it's probably something like that.
The endo thing that you were talking for it.
But is that your set point, or is that like traveling thermocouple data?
I mean, that's the traveling thermocouple data, but it's also related to our, I mean, I don't know if our set points are set for it to do that. But
Okay, and it could be.
It could be a matter of take-off. So
yeah.
Where are you taking in air and where are you taking it away, and
right.
Give you a dip, and if you don't have any heat input,
you
kind of see that.
Okay, yeah, I didn't know if maybe that was related to your endo versus exo energy.
Yeah, it could be, but it also could be just a kill design issue.
Okay.
All right. So the different clay minerals have different dehydroxylation temperatures. The kaolin's right around between 1,000 and 1,100. But it may occur, that's the peak. That's where the water's coming off the fastest. But it can happen over a range, 750 to 1290. The montmorillonite can be a little bit higher temperature, 1300 to 1600. But you see a couple of little steps there. You can see one long, slow weight loss on your initial heating, followed by a smaller reaction later on.
So how will that change the overall, just like performance within the kiln? You can take a kaolin base versus a not.
Well, your cycle's going to be developed based on what type of material you got and how much of this you have.
Okay, so like for our plant, where Mount Realnite is it, like that's what
yeah.
And it's the composition, I think it's like 50%.
Okay.
So
yeah.
Yeah.
So the balance of that's probably quartz, and then you got some bottom ash to give you some big particles.
Right.
Yeah.
And the rest of it's drop material.
Well, that's the bottom ash, yeah.
Yeah. We mix it with stuff from a local power plant.
Yeah.
So I guess my question is, how does this, like, if I was to go walk into a plant, with, like mine, then compare it to, someone who's got like an airlight formation, formation, like what are the big differences that I would see?
You probably wouldn't see it. They would just have their cycle set up differently. So this is information, I guess, explaining why you would see certain reactions in certain places. Okay, so this is later in the preheat. You may have an area where you slow down versus with a kaolin. Just depending on how difficult the body was to fire and how tight it was. But this material is going to hit its soak temperature at a lower temperature than this. Remember, we said the montmorillonites typically fire at a lower temperature. So what's your peak temperature?
We soak, at the end of our firing
yeah.
At 2,000 degrees.
Okay, that's higher than, well, that could be because of the quartz and the bottom ash in the body. But You know, the kaolin body's usually, you know, minimum 2,000 high for a high kaolin body to get any kind of reasonable water absorption. So it would have to do with how quickly you go up, where you might slow down and allow things to happen. But that also depends on how much carbon you got and where the carbon burns.
Okay.
So there's more factors that go into what your cycle looks like than just the type of clay mineral.
No, for me, where I'm at, like the kiln's been redesigned, stuff
Mhm.
moved around, and you know we're putting in some stuff for more firepower and whatever. And it's like
Mhm.
okay, that's changing the design of where stuff was.
Mhm.
So like what are like I guess the flags that I need to look for? I guess that's how it's more.
Well, you would let your properties guide you on that. So are you clearing the carbon out? Are you getting the water absorption you want? What's your shrinkage look like? Those are the kind of things that are going to guide you, and then you would make tweaks based on what you know about the material to get to that point.
Right. Okay.
So I always use the end product as the guide and improve from there, because it's unlikely you could use anything like this and design your process just by knowing these facts. These help you understand what's happening already in the kiln. Does that make sense?
No, it does, and I just taking like this a little
Yeah.
bit and
Yeah.
applying it to my process.
So you're redesigning the kiln for...
No, it's not that I redesigned it.
I know.
No, it's just that it was made a certain way for our
Mhm.
process, and then at some point in the line, like they hacked a bunch of stuff apart and repositioned it, and then now it's like.
Are you trying to get more stuff through the kiln?
Yeah, we're trying to increase rate.
Okay. So it's probably to get more heat in the load.
Yep.
Keep it going.
Yep.
Okay. So again, you got to remember when I show you temperatures like this, these are kinetic processes. So these are an idea of where the temperatures, where these things happen. So if you're putting more load through the kiln, you're going to need more burners around this point if it's a kaolin-based material to make sure you have enough energy available to fully decompose all that kaolin. Does that make sense?
Right. And same
Yeah.
thing for us.
Yeah.
In that.
Somewhere in the 1400 range, you need to make sure that you can supply enough energy to drive that decomposition reaction to the end and keep the product heating.
Okay, and that makes a lot of sense based on some of the things that we've seen
Okay.
in the process.
Good. So we can do some stuff, and I won't go into this too much, but this is something I played with for a while. I wanted to be able to predict the effect of time and temperature. And so this is looking at a material, mainly a carbon burnout and a dehydroxylation. We run it at a bunch of different heating rates, and then I could get to a kinetic model, and then I could basically, if I knew your cycle, I could predict the results that we would get. And the whole idea here is, instead of having these sharp steps, is to try to heat up so that you get a linear weight loss, which is theoretically more gentle. But if you know where nothing's happening and where something's happening, you can go really fast in some areas and then slow down in others. And so it was something we played with for a while. And it actually, we can make a better brick in less time in the lab with those kind of optimizations, but never have been able to transfer those to a real situation. So
that last graph that you were showing, the carbon, is that why that we're not, when we do our moisture readings, when we take them out of the dryer, we don't go over 400 degrees because it starts to remove?
you don't want to start to burn the carbon.
Because it starts to, and that'll change our weight.
Mhm.
Okay.
Well, and you just don't want, I don't think your dryer's designed to burn carbon.
No, I mean,
Yeah.
no, we have a little oven that we stick the
Oh,
bricks in.
that's why,
It
okay.
checks to make
Yeah.
sure, see if all the moisture's out, but
I got you.
we were getting tested.
We have had places where they get the dryer too hot and it starts to burn the carbon.
Oh, okay, yeah.
So.
It was messing our readings up. We were
Yeah.
getting like 0.8. And
Okay.
I was like, that can't be right. The book says 400, so we took a
Yeah.
thermometer. We're like, whoa.
And you back off and then it starts.
Yeah.
Okay, that makes sense. So we've got our water that's residual water that's still hanging around. We've got our decomposition of the clay mineral in the quartz. We've got our carbon burnout taking place, and pyrite's going to burn, marcasite's going to burn in this area also if it's available. And then you get to the end of that preheat, and hopefully you're starting to form glass. So we call that the beginning of vitrification. So our carbon burnout, we've already seen this diagram, but basically we've got to, the thing I think is important here is we've got to find a way for oxygen to get in, find the carbon, and then once it does that oxidation, it's got to bring the products of combustion back out. So as this skin, okay, where it's already burned gets thicker, then the amount of oxygen, or the difficulty to get the oxygen in increases as that core shrinks and shrinks. And if something happens to seal up that outer body, okay, where we make that skin impermeable, we get to the point where we can't necessarily get those products of combustion back out, and you could end up with something like this. So this has, for whatever reason, the skin sealed on this, and whatever carbon was left went and found some oxygen, but once it found the oxygen, it couldn't get out. So here's some examples of carbon burnout, looking at fast heating rates, slow heating rates. So this is increasing organic content. So you can see here we're starting to bloat, but now we've got the sides flaring out on this. Versus the same amount of carbon over here with a slower heating rate. So just by playing with the heating rate and the preheat, you can improve carbon burnout. We occasionally do draw trials where we pull brick out at different temperatures and look at how the carbon's are clearing. So to improve carbon burnout, there's a whole lot of things you can do. So there's a lot of them that are kill or operation design that are sort of beyond what we do. But increase the amount of oxygen, increase circulation, make sure that oxygen is getting to all the brick through the setting, and maybe try to optimize the kill schedule a little bit to give it a little more time for that to happen. Other things you can do is you can try to open up the body, and even though this sounds kind of crazy, some people put sawdust in to make the body more permeable. The sawdust burns and it leaves big pores that will then allow more oxygen in. And there are other ways of trying to form pores. You can use, actually in refractory castables, are typically very hard to dry. I don't know if you use any castables in your plant, but they put little polypropylene fibers in there on purpose. And they get it to a point where the polypropylene melts, runs out, and it leaves little channels for either water or dehydration reactions to take place. Or oxidizers. There are some things we can add to the body that will supply oxygen. And this is one of the cases. I talked about how manganese slowed down a kill with solids. This is a trick we used for red body tile. The manganese goes through, I think, 3 different steps where it gives up oxygen spontaneously. It starts out as MnO2, it ends up as Mn3O4. So this is black manganese, and then the Mn3O4 is the brownish red type you can buy. It all ends up as Mn3O4 after it goes through our kill. But if we need it and the color doesn't bother us, we can use that to help clear a core. So these are all the same body with different amounts of manganese, and you can see how progressively with more manganese getting the carbon out. It's a good trick because it happens to give you the carbon in the parts of the cycle where you need it. So sulfides, theoretically what we would like to do, this is pyrite or marcasite, give it enough oxygen that it goes through a couple of steps and ends up being iron oxide, red iron oxide. That's ideal. Sulfates, again, are very sluggish. They'll start to decompose in your late preheat, but it's very difficult to get them all out. And if you don't, then efflorescence becomes a a problem, but they're just very slow. Carbonates, they tend to go pretty quick. Depending on the atmosphere, if the atmosphere is very high in carbon dioxide, it pushes this to higher temperature. So this decomposition is typically happening somewhere in the late preheat before you get to the soak, and that decomposes and gives off carbon dioxide. So quartz we've already talked about. We've got our alpha to beta, and then on cooling we've got beta to alpha. So there's that dimensional change that takes place. Typically we're not worried about it in the preheat. It becomes more of an issue in the cooling where we've got a glassy phase gluing everything together. And that's where we can get cracking and things like that if we're not careful on the cool.
If you cross that temperature too quickly, does that create problems too?
Well, what really typically causes a problem is if, say, you've got a brick on the outside of the car, and one face is exposed to airflow in the cooling. And so you've got this end cooling off faster than the part of the brick that's buried in the car. There's a dimensional mismatch across that brick. And anytime you get what you call a gradient, you're creating stress.
So this side above it, this side below it.
Yeah. So ideally you want the whole thing to go through at the same time, but that's, of course, not easy to do. So again, just looking at different dilatometer curves for materials with different amounts of quartz. Thermocouples, sending thermocouples through the car can show you a lot. Jim's got some examples we'll look at tomorrow for preheat cracks, I think, where they use this kind of analysis to help them understand. But this is telling you you've got a lot of range in the early preheat. I'm assuming that's top to bottom of the car, but we don't have a legend here. It's just an example. But this is a good way to see what's going on. So what we're interested in when we're looking at the finished product, we can look at a lot of things. We can look at the mineralogy, okay? We can look at how much glass we made. We can figure that out. We can look at how much mullite we left behind for strength. Did we form any cristobalite? What's the residual quartz? Physical properties tell us a lot. Size, water absorption, compressive strength. We can have a good water absorption, but if we screwed up in the cooling, that compressive strength's not going to be there. If we went up and down too many times. How much salts are left? How much of the soluble salt did we not, or the sulfate did we not remove? And then color. Color is a function of temperature, time, and atmosphere. So we can look at those kind of things to figure out are we getting what we want in the product.
So when our absorptions, when we do coming out of the kiln,
Mm-hmm.
we do a top, bottom, on the top, on either side, and
Mm-hmm.
in the middle. Add like 5%, 5%, 4, 5, 5, and then 1 in the bottom middle.
Oh, 1 in the bottom middle?
Yeah, 1.
I'm assuming that would have to be, is it a top-fired kill?
Yeah, top part.
Okay. Does that seem like you're penetrating pretty deep with the heat? Okay. So it would have to be how you're putting the heat in the kill.
You would recognize that
Yeah.
top five kill.
Yeah. Yeah.
So the top part would be put right down at the bottom?
Yeah.
So that it would be a
So I'm guessing it's near a firing lane.
yeah,
Yeah.
right in the way of the firing lane. So that, I guess that there's more fire touching that brick than.
You're getting more heat energy down there.
Okay.
Yeah.
Driving it down good.
Yeah.
So that's not a bad thing. Then,
It may be overdoing it a little bit.
The lower
Yeah. Yeah. For 1%, because you don't want it to stick.
yeah.
You get a pretty big range in color if you got 1% to 5%.
Yeah.
I need to
Some adjustment and yeah.
And it's all about uniformity.
Yeah.
You want uniform top and bottom side to side.
So this last one's just a summary of some of the stuff. So Jim is getting an XRF unit, so we could use that to tell us what's in the raw material, but more importantly, how consistent is the raw material? Is it the same amount of alumina, silica, sodium, potassium, iron going in? Because if you've got variation in that iron content, you're going to have variation in color. So to me, this is a fundamental thing, along with particle size, that you can watch. Loss on ignition, like we talked about, can tell you a lot of stuff about what's going on in your raw material. Big changes in that can be a red flag that you need to go look at other things. Mineralogy usually only comes into play when you're trying to solve a problem. So that's one of those backup kind of things we do. We don't understand why a material is acting like it does. We may resort to that. We do this test. We have a specialized test on the X-ray where we can put a number on how much quartz is in the raw material. And we do that quite a bit, and that can be one of those raw material consistency tests. But it depends on your raw material. Is that a problem? Does it ever get too high? That's when you have to look at that. Carbon and sulfur, again, if one of those tends to be high and you may have a problem with coring or something like that, you may want to watch that as a quality control tool. Dilatometer, usually that's just looking at new raw materials. I got in a sample now where somebody's gone into a new pit and the brick were sticking. So they want to find out, how different is the new material from the old material, which I would have wanted to do before I put it in the kiln. But so we're doing tests like this to see, where the onset of vitrification is for the new versus the old. Insoluble salts, if scumming or efflorescence is an issue, it can tell us how much is there, and then it can be used to calculate how much barium carbonate is actually needed. So we do those kind of things, and we'll talk more about firing tomorrow, so come with your questions.
Okay.
All right, so let's talk about color a little bit. So remember yesterday we talked several times about how almost everything we deal with is a function of temperature and time primarily. Well, when you bring color in, you got to throw in atmosphere also. Atmosphere is also important. So those are three things from the kill or your process. But we got to start thinking about material also, and how consistent the material is, how consistent the extrusion is, even how tight the body is. So let's start going through this. And I probably need to turn that guy on. All right. So factors that affect color. People. And I would, we'll come back to people. Materials. We'll talk about all of these as we go through. Equipment, process, and people tend to focus on the kill because you see the color coming out of the kill. Just like efflorescence, the efflorescence in a wall shows up on the brick, so people automatically assume it's coming from the brick. They never think about the mortar, okay? So wherever the product was last, that's what people like to point their finger at. But there's a lot that goes into that, and let's start thinking about all of those. So the most important thing we consider from the raw material point of view is the amount of iron we've got. That's going to determine, what kind of color we're going for, whether we're going for a buff or a tan, or we're going for a dark red brick. And one of the things about that iron oxide, we can add iron oxide to try to modify a color, make it darker, but we can never really imitate what Mother Nature did. The way the iron's incorporated naturally in the material gives more coloring power than anything we can do with adding it. We just never can quite get the same result. The other thing, though, to consider with that is you can't take iron away. If the iron's already in the clay, you can't make it a light firing brick. Okay, it's going to be a dark firing brick. What's there is there, and you have to live with it. So usually Jim Frederick, who some of you've met, colors his thing. He did all of it. His schoolwork when he was at Clemson, he worked on color with Dr. Robinson. But he's saying the iron oxide content's got to be above about 2% for a red brick. That's probably on the low end, but anything below 2% you can get other colors out of. But for a deep red color, you want about 6 to 7% iron oxide. And remember, we looked at some chemical analysis yesterday. There were some that were in the 4s to 5s, and then there was one that was a 7 or an 8, and I pointed out that would give you a nice red color. So that's one of the things you can look at. So if you are doing raw material testing, I was talking about looking at the silica and the alumina and things, you know, kind of understanding how the material is going to fire. Looking at that iron content is going to give you an idea of consistency of color. Okay, part of the color equation, but it's going to let you know if a deep red is possible or if you're going to see variation in the color. And you know, I deal with a couple of plants where color is a real big deal, and they don't have really great control of atmosphere in the kiln, and they get dark and light and dark and light, and they keep thinking it's the material, and so we keep going to look at the material, but when we do chemical analysis, the iron content's pretty steady, and you have to come back to the fact that it's atmosphere related. So all of this goes together when you're looking at color. So in natural materials, the iron is in the silt or the sand fraction, and it's distributed in a way that gives it a very nice coloring power compared to if we try to add a synthetic iron oxide. We typically don't get the same kind of coloring power or coloring effect if we're adding an iron oxide after the fact. So it's generally in the really fine, in the fine part, gives you the most coloring in the clay fraction, but you can have iron spot materials. So you can have your siderites or some iron hydroxides that can give you an iron spot that are in the coarser fractions. So, but like I said, most of the fired color is due to the really fine part, and it's really hard to duplicate. So other constituents influence color. Color is going to be in some respects dependent on how well the brick is fired. Okay, so for a given amount of iron, the more glass you make, the color is going to get progressively darker. Okay, we'll look at some gradient firings at the end. This probably would have been a good point to put one in. But as you look at firing harder and harder, typically you see a color change. And some people like to use color as an indication of how well something's fired, but that's not necessarily a good thing. But you can darken your color if you want to by, you know, you can either add something that fluxes the material, or you can try to get a little lower water absorption, and you can get a darker color, and you can lighten it on the opposite end. The clay compounds like calcium actually bleach out the iron color, or the red color. So if you have limestone or a high lime material, you're going to get kind of a dirty yellow color out of it. It's just lime reacts with the iron to form a new compound that doesn't have that red color. So things like this can actually bleach out your color if you're trying to make a red brick. So temperature is important for a couple of reasons. Like we just said, it influences the amount of vitrification or the amount of glass. Usually more glass gives you a darker color. But it can also influence the iron compounds. So if you remember, we talked about Fe2O3 being red iron oxide and Fe3O4 being the black iron oxide. So this is hematite, that's magnetite. Okay, you think magnets are black, that's how I remember it. So as you fire hotter and hotter, there's a natural conversion, and it's slow, it's not 100%, but at higher temperature, this form is favored over this form. Okay, so you lose some oxygen from your Fe2O3 to make this Fe3O4 naturally. So that also adds to darkening as you fire to higher temperatures. So two things are going on, just to make that clear. Vitrification usually makes the color look a little darker, increased vitrification, plus you get some natural conversion of the red iron oxide to the black. But this is also dependent on atmosphere. You can accelerate this by changing the kill atmosphere. So high temperature, basically what we're saying, when you convert from this to this is called a reduction. We won't really get into that. That's from high school chemistry, and I always hated that part. But you get a natural reduction as you go from the Fe2O3 to the Fe3O4. So the kill atmosphere also can influence color, air to fuel ratios. So like we said, this is a reduction. And I can't spell, especially on a board. So we can promote that by having excess carbon monoxide in the kill atmosphere. And we do that basically by putting more fuel in the kill than the air that's available to burn it. So when you flash, what you're doing is basically you're trying to create excess carbon monoxide in the soak zone. And that carbon monoxide wants to pick up oxygen, and I won't bother balancing this, to make CO2. And if there's not oxygen in the kill, it takes it from here. Okay, and that's how you go from the Fe2O3, you reduce to the Fe3O4. So some of this happens naturally, and then some of it, if you're flashing, you enhance it basically. By the more CO you can make in that kill atmosphere, the more of this Fe3O4 you'll make. Okay, the darker the color you'll get. So a little bit happens naturally due to temperature. A lot happens if you flash and you create carbon monoxide and force it. And I've been, there's some brick manufacturers that are really famous for making very hard flash brick. Anybody ever seen an Endicott black brick? Okay, it looks like a piece of metal almost. Yeah. I had to do a bunch of carbon monoxide measurements at one point for a study we were working on. And I was on top of one of their kills because they flash continuously. And I started feeling really bad. I got this really bad headache. And then I started looking at the meter, and I was like, oh, I need to go outside for a little while. It was like 400 parts per million of CO, which is actually dangerous for a long period of time if you were standing right on top of the kiln. Now, if you were on the plant floor, it was okay. But just something to keep in mind if you're ever working around flashing. Be aware of the atmosphere, because you're intentionally creating what you don't want to happen in your home if your furnace isn't operating correctly in the winter. Solid fuels, you can dump in coal or things like that, and basically all you're trying to do is take up any available air and have more fuel than you have air to burn it. Saltillo tiles, the ones that give those kind of yellow colors, light reds and yellows. Do you know how they make that yellow color? To get that yellow color, you need zinc. Okay, so they dump chopped up tires in the hot zone of the kiln, and the zinc in the metal in the tire, the what do you call them, bands? Yeah. That produces enough zinc in the atmosphere to bleach out that yellow color. So you have to have chopped up tires to make Saltillo tile. It's actually pretty interesting. Flame impingement. You can get some weird colors if you have direct flame impingement on the brick, but you got to be careful of that. You don't want to stick the brick together. And flashing gases. So basically, this is the same thing as here, where we're trying to produce excess fuel so that we make carbon monoxide and don't have enough air in that kill zone, so that we have something that's trying to take oxygen away from the red iron oxide. And then the total amount of vitrification. This is a repeat of what we had before. More glass usually means darker color. And that is influenced, like we talked about yesterday, by the raw material, the amount of the alumina-silica ratio, the amount of fluxes that are in it, any additives we might add. One of the additives we talked about yesterday was town ash, they call it. Basically, it's just the solids left over from water treatment that have been burned, and it's got a lot of potassium in it. Tends to be a good flux. We've looked at that before. If you can find a good source of it, ground up recycled glass, because there are mountains of it around a lot of cities where they take it in, but they don't know what to do with it. It doesn't actually get recycled. If we could get that ground up, that is an excellent additive for brick, because it does a couple of things. Some of you calcine your material, right? Mm-hmm. Okay. It would be similar to that, but remember we talked about material having to go through endotherms in your kiln? Well, you've just taken that out. Okay, any of those reactions, you've already made them go away. And glass, for example, has been fired to a hot enough temperature. We'll talk about emissions later, but they've fired it hot enough. They've driven off the fluorine, the chlorine, the sulfur. So it's a clean additive. So if you add 10% glass, you just dropped your emissions 10%. So that's one of the things I love about those kind of additives, is that it can help us with our emissions as well as dropping our firing temperature, maybe saving some money. So that's one thing I'm always on the lookout for. But vitrification is also influenced by atmosphere. And we'll talk about that in a little bit. But reducing atmospheres, if you make anybody make the same product flashed and not flashed? Yeah, okay. When you look at water absorption, which one has the lower water absorption? The flashed always does, because you're dropping the onset of vitrification with the carbon monoxide promotes glass formation. And it can drop it pretty significantly in some cases. So you get a natural darker color just from that, because you've promoted vitrification. So more glass, the darker the color, like we've said. One of the things, and Jim worked a lot on this, but it is possible, given the right conditions, you can get that dark flash color, and then you can reoxidize, and you can go back to the red color. Iron will change a lot, especially at high temperature, and it's very sensitive. And we'll talk a little bit about where that can happen in a minute. So we've already talked about the iron oxide, the reducing conditions. I don't like these words, but the red iron oxide is a ferric oxide, and then the black iron oxide is a ferrous iron oxide. It just has to do with your high school chemistry and the forms. So along with time and temperature, we can make these little clusters, or color centers sometimes. We talk about the iron oxide, and that's how all colorants work. So if I'm making a glaze and I want to make a blue glaze, and I add cobalt oxide, which is really expensive, to the glaze to make the color, I get these little scattering centers, they call them, and that reflects the blue light if it's cobalt, or red light if it's red iron oxide, to give that color. So if you remember yesterday, we looked at an SEM picture, and there was a little bright spot in the corner, and I said that was an iron oxide cluster. Okay, that's what's giving us the color, those little spots with the colorant. So this is just a repeat of what we've talked about before, but temperature, time, degree of vitrification, all there can influence the color. So when we talked about firing originally, when we talked about raw materials, we talked about the raw material has to have a sufficiently wide firing range to give us uniform properties within our ability to control temperature. And this is just another way of saying that. Some materials have a very short range that give a uniform color, and some have a longer range. You can see that in the gradient test, and we'll look at some gradients in just a minute. Actually, there's some we did for Acme, helping out Huntsman, but you might recognize some of the stuff. And then this natural reduction of the red iron oxide to the black that happens above 2,000 degrees. It's slow. Usually, if you want to get a good conversion, this is another way of writing out Fe3O4. It's basically a solid solution of these two. You don't really need to know that. But let's see. So you get some of this occurring naturally, and you can enhance it by doing the flashing like we talked about, where we put excess CO in. So in reducing conditions, if in the right conditions, and you can get different colors based on where you do the flashing, and we've got a slide coming up on that. So this is the normal flashing reaction where we've got the red iron oxide plus carbon monoxide that we're producing because we've got more fuel than we have air. We don't have the correct blend when we flash. We make some FeO, and remember Fe3O4 is a mix of FeO and Fe2O3. Gives us the magnetite, plus CO2 in the atmosphere. So another way of saying that is this carbon monoxide wants this oxygen more than the iron does. Okay, so if you get it hot enough, it'll take the oxygen away from the red iron oxide and you get the black form. You can also do the same thing in the right conditions with hydrogen gas, although I don't know why you'd want to. But some people who do work in the metals area, they do use hydrogen for reduction. This is one of the most powerful reducing agents out there, but it's also not very stable to work with. But you mix hydrogen gas with iron oxide, and you basically form water. Water is one of the most stable compounds there is. So any way it can form, it will steal oxygen from just about anything to make itself. And it can be a very powerful reducing agent. It's just not safe to work with. You can do it with carbon, a solid fuel. This is what happens in a bloating reaction, where there's residual carbon left. You reach the temperature where this goes back to something we call thermodynamics, but you get to a certain temperature, this carbon wants this oxygen more than the iron oxide does, and it'll take it away, and you can form CO or CO2 depending on how severe it is. And ideally, that gas can escape. If it's not an ideal situation, it can't escape. You make something like this. Okay, so basically bloating is sort of a internal flashing reaction, if you will. So when we reduce, the black iron oxide is a mix of the Fe2O3 and this FeO, and FeO can act like a flux. It's called woostite, and iron can exist in a couple of forms, and so we can have FeO, Fe2O3, and Fe3O4. We can also form coloring clusters, and we actually form this quite a bit in the body, but we just don't ever talk about it. This is a compound called phaolite, and you get little spots of phaolite where the iron reacts with silica and gives you the red color. So that's typically inside the brick too. So normally we're making that at the end of the preheat zone. And the magnetite or black iron oxide we're forming in the soak zone if you do a flash. So we've got different coloring zones, and the following slide we'll talk about what kind of colors we can make in each of these. So we've got two in the preheat, we've got our soak, we've got our first cooling, second cooling, and third. So if we look at this is a little hard. This is zone 1, so remember we're talking right in here. Reducing conditions cause red clays to form brown or tan shades. Okay, and this depends on where you make that. When we're in the second zone going up to the soak, we start to make that FeO and phaolite, so we can get green to black colors. And I always noticed on these, when you look at this, and I'll pass it around, there's always a little green rim right around the edge, a faint green color when you look at these, if you want to take a look. In the soak zone, in a clear burn, we make clusters of that red iron oxide. Kaolins that don't have as much iron tend to go a little pink at that point from the iron that's in the clay mineral. Illite may need extra oxygen to get you good red colors. Flashing gives us additional phaolite, plus it gives us magnetite. And you know, there's a range in all of this. You see a whole range of colors typically when you flash. That's what makes it so beautiful, is it's not a uniform color. It depends on how the atmosphere was distributed in the kill. Lime can start to form compounds here. There's one that's called anorthite. That's what gives you that bleaching or yellow color. And then you can also form this thing called sphene. This is why when I told you I tried to make a porcelain and all I could make was browns, I was doing something like this except with magnesium. So in zone 4, right here, so the first part of cooling, that's a reoxidation. So colors of browns to yellow can be achieved if reducing conditions are maintained in the soak and oxidizing conditions in the cooling. So depending on what the atmosphere is like in the cooling, we can start to change some of that soak. Reoxidation 2, this is that short range right here, okay, from 19 to 1850. We can get really bright reds in reoxidation there if we allow that. And then going down further, we can get pink to gray colors if we do reducing toward the end of the cooling zone. So different zones can give different colors for the iron. You can make a whole range. So factors determining flash color, this is sort of a repeat. The makeup of your material, where it fires, how much glass you get as a function of temperature, airflow controls in the kiln, how you move those flashing gases around, position of the reduction zone in the kiln, and what they're talking about is where you're doing the flashing. You get different colors depending on where you try to flash. Flashing temperature and time, how hot the gases get, do you make more glass? The reducing agent, typically we're making carbon monoxide, and reoxidation temperature. So where do we convert back to an oxidizing atmosphere in the cooling zone? So a lot of these, this one, actually Jim Frederick was co-author on this. These are in American Ceramic Society. If anybody wants any of these, I can pull that article up. Plus there's articles Jim's written in our magazine that are available on that brickandtile.org that I was telling you about. I'll write it down. And all of you have access to that. Plus, there's WikiBrick that you access through our website. So make sure if you're interested and you want to learn more, it's all there. So problems with flashing, and I don't operate a kiln, so I'm going to tell you what Jim said. I'm not an expert on actual operation. I can tell you from a material point of view what's happening, but as far as how to drive the kiln, that's outside of my expertise. But this is some of the research Jim did as part of his master's. He worked on all this color stuff with Dr. Robinson. So problems with flashing, lack of consistency resulting in color variation, sticking, high shrinkage, low absorption. So we're making more glass, so we get higher shrinkage, we can get sticking or low absorption. So one of the things we looked at is what actually happens to the raw material when we do flash. And we did some tests in the lab where we simulated flashing atmosphere. And we looked at what the potentials were. Especially, we were interested in what it does to soluble salt content and efflorescence potential. Does it make efflorescence worse? Because remember, we talked about there are two things for efflorescence. There's how much salt is in the body that can potentially cause efflorescence, and how easy is it for the water to get in and find that salt and bring it to the surface. So theoretically, when we flash, we're closing up the pores and we're making it harder for these salts to be found, but at the same time we may be leaving more salt behind, and that's some of what we did. So we've already looked at some of this. These were the raw materials we looked at. We've already talked about different clays and shales, carbon content, sulfur content, soluble sulfate. So generally, when we're looking at this column, anything over 100 parts per million, we think of as sort of a red flag when it comes to potential for efflorescence. So we looked at different atmospheres in the kiln or in the lab. We did a clear burn, basically 20% oxygen, just like the air we breathe. Our reducing agent was CO, and we were able to buy gases, bottled gases for use in the lab that had different carbon monoxide contents. So these would be a flash through the whole firing. We can't really simulate changing the atmosphere like you do in the kill. So we basically fired the whole product under these kind of atmospheres. So a low oxygen, we fired at 2%. Neutral, it was all nitrogen, no extra oxygen available. And then you go reducing, it's 10 part per million of CO, not very strong reducing atmosphere, and 350 parts per million of CO, moderate reduction, not that much. We're getting ready to do something for one of the kill manufacturers where we bought 5% carbon monoxide and CO2, and we're using that for a simulated firing for him.
How would you, is there any way to measure that in the kill? Or?
In the kill, yeah. You have oxygen sensors.
Well, yeah,
just like oxygen, you can buy CO sensors. I don't know if they're high temperature, because the high temperature oxygen are usually zirconia, and they work on a different principle. What we do when we're looking at it is we actually look at the exhaust gas. So we have like a testo unit. I think you have one here.
We have a testo that will measure carbon monoxide.
And it's actually...
But not in the kill.
You actually can go in the kill if you've got a long enough probe.
You got to make, I don't know what Francisco's the expert.
No, our probe is about 12 inches, so it won't go all the way down.
Okay. But we've done it in the lab kill, but it's got a cooler and a condenser, and it cools the gas off before it analyzes it.
Testo is pretty high temperature, but not that high.
Yeah.
Not a couple thousand degrees.
Right. We've done some stuff with directs in the lab. We're in our shuttle kill. We've been able to stick it in and get an atmosphere reading.
Yeah.
But having said that, it's currently the condenser unit's out for repair. So we might have overloaded it. Yeah. So what happens to the residual sulfur content? Well, when we're not in oxidizing atmospheres, as we go more reducing, we tend to leave more sulfur behind. The only way we're getting rid of sulfur for the most part is when we're doing this clear burn on most of the materials. And when we leave that sulfur behind, the higher that residual sulfur, the more potential there is for efflorescence. The soluble sulfates, actually we moved away from soluble forms of sulfur to more insoluble, which doesn't make a whole lot of sense. But we had the highest soluble sulfates in the clear burn, and reducing they were less soluble. So potentially, while we're leaving more sulfur behind, we're possibly leaving it behind in a form that may not contribute to efflorescence. So we'll skip over that. So onset of shrinkage, this is a little choppy. So this would be the clear burn, the neutral, and then looking at the reducing. This where the onset of shrinkage drops, but then seems to come up. This is telling us the material bloated. Okay, so we started to bloat, and it started to puff up on us. So in general, most of these we see a decrease. This one material, we saw a big decrease just going to neutral, where it starts to shrink at a much lower temperature than it normally would, and then it keeps. You don't get as big of a reduction as you go to that high reducing content. But basically, this is why when you see a flash brick having a lower water absorption, because we're promoting the glass formation. We're causing it to happen at an earlier temperature. This is an example. This is one of those materials. These are the dilatometer curves, remember? So we're heating up. We go through the dehydroxylation or the decomposition of the clay mineral, a little bit of quartz inversion. This is the neutral, and then the reducing. You can see that they start to shrink at an earlier temperature. Remember, this is temperature down here. Then this red line, which is a clear burn. And then when you see them start to grow like that, that means they're bloating. Okay, so this one's continuing to shrink. These guys are saying they've got enough stuff trapped in them that they're trying to bloat. But if you use this 2% shrink line, here we can see we're, 1950 roughly. before we get to 2% shrinkage. And in this one, we're more like 1800 or less to get to that 2% shrinkage. So a lot more shrinkage at a lower temperature. We also see increased shrinkage as we go from the clear burn here to the reducing, but we did see some effects where it started to bloat or something like that. These two bloated, the green and the blue, started to puff up on us. Oop, got ahead of myself. All right, porosity was all over the place. In general, we see a decrease, but like these guys where we had bloating, and then some of them just started to really fuse on us, and the absorption dropped way off. You also have something, when we talk about porosity, there are two types of porosity. There's open porosity water can get into, and there's trapped porosity that's basically like a bubble that doesn't have an opening to the outside. I think some of this we might be seeing trapped porosity where the water just didn't have a way to get into it. So typically with flashing, onset of shrinkage is lower. You see more shrinkage. You can see bloating. And you're doing a lot of changing to the form of sulfur that you're leaving in the body. So this is some examples Jim put together. Plant example, color range in a new material. So this is an example of how chemical analysis can help you. Most of the time we get called in on these after the problems occurred. And they say, well, our material changed. Well, unless we can see the old material and compare it to the new material, it's hard for us to tell you what's happened. In this case, we had examples. So a couple of things going on here. You notice the old material had more silica. This one, remember I told you alumina is usually an indication of the clay content. It also appears to have more clay. We also did a particle size, and the particle size agrees with that. So the old material was more sandy. The new material has more clay. The other thing you notice here, remember we talked about the fluxes? The new material has a lot more flux, so it's probably got a lower firing temperature. So we're going to automatically be darker if we're still firing at the same temperature. Plus, there's a difference in the iron content. So the new material's got a higher iron content, so it's probably a lot darker because we've got more fluxes and we've got more clay. Remember, we talked about where that colorant was made a difference, and we have more iron. So a lot of things going on there, but all of them are kind of steering us to the fact that this guy's going to behave a lot differently than this one. So just an example of where looking at your materials can help you out. And then these are some examples of doing gradient work. I can't remember which plant this was, but it's one of the it's an Acme plant. But basically, this is a raw material by itself, going from roughly 1750 to 2100, or somewhere 2000 to 2100. We don't have the actual temperatures on here. And that's the kind of color range you see as you fire harder, okay? So we're changing the form of the iron a little bit, but we're also getting more glass by the time we get out to here. This is 1% of a synthetic iron oxide, so basically you can compare down the line, 2%, 4%. This would be the lowest firing temperature, and then the temperature is progressively increasing to this end. So you can see the color difference, and by the time you get out to this highest temperature, and again, this is a picture, but there's not a whole lot of difference between the different iron contents and the color. Same raw material, different iron oxide, basically showing the same thing. Lowest firing temperature, highest firing temperature, and then we're increasing the amount of iron oxide. And then yet another iron oxide. This one's given more of a sort of purple look to me. In the raw material, but you can compare from the lowest firing temperature to the highest firing temperature. And another. Any thoughts on color? Any questions? No? All right. Mike's going to come in, and I think we're doing, I can't, refractories next. So he's going to give you just a quick introduction to refractory terminology.
I'm not here. Oh, sorry. Answering the phone. Take a quick poll. How many have worked or are working in the kiln area? Woohoo! Okay, so you guys probably know more about this than I do. We're going to talk about refractories and just some things to think about if you do have to do repairs on the kilns, especially if you're looking at different products to put in there. There are things that you do need to think about. There are also things that our lab can help you with understanding if you are trying a new material or you believe there is an issue with the refractory that you're using. We'll be more than happy to help you with. There are some inexpensive quick tests that can be done, and then for further investigation we can usually help you find what the source of the issue may be. For this presentation, we're going to split it up into a couple of different sections. One of the things that we want to promote before even starting, that if you do have refractory that you're keeping around for doing repairs on the car decks or repairs on the kiln, it's typically never a good idea to store it outside uncovered, just because it's going to get exposed to stuff and you're already going to start degrading the product before you even get to use it. You got to remember that the refractories are created for something that's completely different than what facing brick. They're not meant to go outside. They're not meant to be put into freezing environments or anything like that. So they're, from that standpoint, they're much weaker. So you want to think about that if you have materials, get them covered, get them protected. For this, we're going to look at basically the definition of refractories, how to look at product sheets and understand a little better what you're looking at, castables, and then also fire brick, mortars, and ceramic fibers. Refractory is basically refractory. You're putting it in there to keep the heat in and keep it from leaving the kiln. So the more refractory a material is, the less BTUs you're going to have getting out of the kiln typically, and the less energy it takes putting into the kiln to actually fire your product. At the same time, typically that's inversely related to how robust or rugged the refractory is. Unless you get really, really expensive refractories, which typically we can't afford to do. That goes into, which you'll see in a minute, more driven by density of the product. That I'm sure you guys have picked them up, and if you pick up a 2,000 degree brick or a 3,200, oh actually you guys probably don't get 3,200 degree bricks in the plants, or do you? Anybody?
Different applications.
Correct. I mean, it's basically, when you look at your kilns, you're not going to, I haven't come across one yet that it uses the same brick on the outside of the kiln that you use on the inside of the kiln. You're putting the more dense, robust, heavier harumph brick on the inside that can take the abuse, can take the higher temperatures, that can take the chemical attack better than what you put on the outside. And the outside typically have the higher R values or the less thermal conductivity. So it holds the heat in more, and the inner is kind of like a protective shell on it that can take the temperatures. What you'll see the term, the PLC used in here, which is permanent linear change, and that is when you heat it up, it's going to shrink. It's going to expand first, but it's going to also shrink. And it's sometimes it's due to the people that are producing the product don't fire it either as high a temperature as you're actually going to be used, that it's designed to be used, but they're trying to get it produced at a reasonable cost, but they don't necessarily fire it to the temperature that you're going to be taking it to. So it's going to finish out its shrinkage when you actually run it. And that's where looking at the sheets to understand what product you're actually getting ready to put in here, what kind of design criteria that you need to keep in mind when doing that. And again, you're talking about these are being mass produced, so just like in your kiln, you have differences within the hack. They're going to have most likely differences in their process too, but they're trying to hit a narrow specification just like you're trying to do, and they're going to promote that in their specification sheet. Hard bricks, again, are typically manufactured through extrusion or dry pressing. Castables are the mix that you get that a lot of you use on car decks or just strategic places that you can't get a formed brick easily to satisfy the location. Insulating brick are typically duty rated or service limited brick to where they're not meant to be abused, but they give good properties when you actually have them in more protected parts of the kiln. Fiber products are typically for parging and repair materials. There are also quite a few kiln systems that use fiber, but there are things you have to keep in mind when working around fiber as well, that the kiln may look beautiful when you put it into service, but when stuff starts coming out of your brick and reacting with it, it can get nasty. And then mortars. This is just giving some examples of the breakdowns of the different product types, and there's a difference in how it's laid out from North America to Europe, but they're in essence the same types of grouping. Fired brick, you're looking at typically a permanent linear change of less than 1% at 2910 for Super Duty brick. The rest of them, you're classifying it by the amount of alumina that's in it, to where you can have 50, 60, 70, 80, 85, and 90% alumina. And of course there can be some variations from that, but that's the more alumina you have in it, typically the higher temperature you can go to, because that's the stuff that's alumina. The previous company I worked for, the high purity alumina parts that we were making were 99.98% alumina. And we would actually fire it to an equivalent temperature of 3,600 degrees to actually fire the stuff. And when you will know if you see high purity alumina, because it's not white, it's actually yellow. Then under insulating brick are typically lower density brick, but you'll see group ratings of 20, 26, 30, 32, and it's relating back to the percent alumina that's in it, the density of the brick, and then what the use temperature will be. And what you'll find is typically this number is correlating to what range of temperature that it can be used. And there's also, I've bought 28 brick as well for kiln applications. Plastics, these are all tested under C673, and again it's more based off of alumina content that's in the material that you're using. And castables, again, it's looking at performance and linear change when you put it into service. That's what's separating out the grades. And again, under the European standard, it's roughly the same thing, just in metric. Key points: shrinkage at service temperature is bad, mainly because when I'll show you in the sheet as you're going up, when you're looking at the properties of the materials, you have to remember that basically almost everything, when you heat it up, it's going to want to expand, because you're putting energy into it. And what in essence what you're doing, everything that's above absolute zero in physics terms is moving. So table, all the atoms in it are moving. As you heat it up, the more moving you get. And when you're firing your brick, you're getting it to where you're creating so much friction in between the atoms that you're starting to basically melt the glass and break bonds and get it to where it starts sticking everything together. Same thing with refractory, to where you're taking it, you're heating it up, and as it's starting to move, since the guys aren't sitting there anymore and they're starting to jump around, they're also getting further apart. So everything starts expanding. When you go through and build your walls or repair your kiln, repair your car deck, one of the biggest things you have to think about is when it goes in at room temperature, it's going to be bigger when it gets hot. So if you're building a wall, you'll see in the let's see if we got the sheet. Well, we'll go through this and I'll jump ahead to that. Bricks are used for their consistent nature, but castables may be more convenient in cars, again, because of the complexity of design or just the general layout of the car, or even time-wise, rather than having to cut brick, try to fit them in, or get them around structures. A lot of times people will go to castables. What makes clay-facing brick work is usually about 180 degrees out of what makes refractories work. So how you fire and use brick is very different than how you fire and use refractories. And then refractories are covered in the ASTM standards, so there are standard test methods that we can use to help identify whether the brick actually meet what you're buying, what the supplier is saying that they're giving you. Looking at the data sheets, what I was starting to jump ahead to, there are some numbers that you want to look at. Bulk density is probably the easiest, and I think I even have it later on. Bulk density is one of the easiest things to test for that will give you an idea of, are these brick what they're supposed to be. Some brick, even just going through picking them up, you can feel the difference, especially on IFBs, on insulative bricks, to where you can tell this is a 28, this is a 24, because the 28s are heavier. And you can tell from looking at it, and even color. If you get a box of refractory in and start unboxing, it's like, well, those are darker than those. That should be a telltale sign right there. Okay, we need to get these tested and find out why is the color difference between these two brick. And it could be the supplier mixed in the wrong brick with it, which I've had before, or they didn't process it correctly. So thermal shock resistance, that's some of the information you're looking at on just the property sheet is alumina content. Again, typically higher alumina, the higher temperature, which this one there's not much difference under load, deformation, cold crushing strength, thermal expansion. That's one you have to pay particularly close attention to, because again, you're in your doing a rebuild, say you have to replace the wall section in your kiln, it's 10 feet long. What that's telling you right there is that 10 feet, when you heat that thing up, if you start getting up to 1,000 degrees, it's going to grow by about a half an inch in length. And if you don't have gaps in it, physics usually takes over and it's going to find a place to go to. And usually that's out from the wall surface. So your wall will start to bow out and it'll start to push the brick out, it'll start to crack the brick. So there are properties in here, again, the bulk density. If there's a question of, okay, are these consistent in the brick, you can take samples, send it to us, and there's an ASTM test for doing bulk density for determining off of 5 bricks what the variation is and compare it back to what they're advertising. And if it's different, then you can go back to the supplier and say, okay, well, what are you selling me? Because this isn't what you said you're selling me. Before you get it in the kiln and say, uh-oh. Thermal expansion. And then also the thermal conductivity, that's going to be just giving you an idea of how much heat is actually leaving the kiln, or how much resistance it has to heat flow going through the walls. And then this has to do with size differences, and again, just like anything, when you're laying it up in the car, if the sizes are all over the place or putting it into a wall, it makes it much more interesting trying to get a flat, even wall. Okay, now go technology on you. Anybody seen these before? Phase equilibria diagrams? What this is telling in a nutshell is there on the materials like this one is magnesium silicate and cordierite, that a whole lot of testing and studies were done to show at different, these are the percentages, so if you're on this side it's 100% cordierite, if you're on this side it's 100% magnesium silicate. When you go through and produce a 20% mixture and start firing it through the temperature ranges, this is basically the breakdown of what you're forming as you're firing it. And it's the same thing on this. This is a ternary phase equilibria diagram, and it actually has magnesia, alumina, and silica. And all of this, it took a lot of work to produce them, but all of them are showing you all of the temperature ranges, and this is actually the most stable part from a thermal expansion standpoint of this mixture, and then you can actually plot out. This one's showing this S55 material is actually over here, which isn't in the sweet spot, but you can get an idea of how much thermal expansion you're going to experience with the material and where you would actually like to be with the material, but there's other properties that you're also trying to balance with it. So that's kind of what they are doing to produce the product that they're selling to you and saying that it's the best product in the world. Why check the density first? Well, for one, it's easy. The stated bulk density was 2.15. The cost of the density experiment is like $50. And then basically, a low bulk density is the first place that something's going wrong with the brick that we're supplied to you. Why could the bulk density be low? I mean, they could have a particle size off, chemistry variations, firing variations, and the degree of impact that it could have to you when you put it into service. Because again, if the thermal conductivity of the brick is higher, you're going to be evolving a lot more heat out of your kiln, which means you have to run your burners hotter, and it can also affect your heat distribution in your hack as well. Because if the outside wall is pulling heat out and you're putting heat in, then that's actually going to drop in temperature on the outside of the package, and you may not get the circulation pattern that you want. And especially if you do a repair, because now you can have unevenness in your walls and be fighting that as well. Properties related to performance. This is showing a plot of, again, product that you buy may not necessarily be fired to the ultimate temperature that you want to use it to. And when you go through it and use it, it's going to expand as you're heating up, but it could also start shrinking. If you use it beyond the temperature of what they fired it to originally, it will most likely start to shrink. And this is just giving you some instances showing you that this is without deformation exhibited with the onset of 1380C. But you can see that it's going through and starting to shrink once you get beyond the temperature either rated to or that it was fired to. Also, properties related to performances. On a lot of applications, you're going to be putting a load on this. And as you heat it up, its strength is going to change. Typically, it will drop. And you need to make sure that when you're looking at a possible replacement product, that it's actually rated. And there are ASTM tests, too, for testing the creep and yield of the refractory block. And this is just showing you some of them here for testing of where you put it under load, put it under temperature, and see what the deformation of the product is. And this is showing you a performance of the linear change versus time at temperature. And by all means, if anybody has any questions or anything, please stop me. I know I'm going quick. But also properties related to performance. This is showing a sheet that basically is giving you, they've done a long time hot load test of 100 hours with a 25-pound load to give you an idea of what the actual percent change is at 2450. And again, these are all things that are nice to know and compare to what you're going to be using at, and think about, okay, is this supporting all of my brick, and what does it relate to what I already have in there if I'm not replacing everything on the car? Because if one side starts to give and the other side doesn't, it can get kind of interesting. Thermal shock resistance also, that's part of the balancing act that these guys are doing when they're making your refractory, is they're trying to make them robust, because your kiln in general stays at a relatively constant temperature. You'll do some shifts depending on the product line, but you're not going all over the place. The kiln cars, however, are going through, and again, yours aren't as aggressive as other product lines for how fast the temperature changes. However, one of the things you have to think about, if your car is below deck fired, when it goes past that first burner, it's going to get a surprise. So it needs to you need to make sure that the thermal shock resistance of the product that you're putting in those locations are robust enough, because again, when it grows and shrinks, not necessarily everything, just like in your brick, is growing at the same rate, to where the temperature has to get into the center. So typically the outside is going into tension because it's growing faster, and then, or excuse me, the inside's going into tension, the outside's going into compression because it's growing faster, and that puts stress on it, and you will induce cracks in the refractory. So you need to think about, okay, how is this going to affect me? How am I using it that can cause an issue if it's under load later on? This is showing a graph of just a number of air quenches on the MOR. So looking at that 3-point load modulus of rupture of breaking the brick, just after the first, wrong way. The first cycle, you've induced cracks. So now your MOR drops. And then consecutive cycles, you're inducing more and more cracks. It doesn't drop as much, but it's still cycling and weakening the structure. And of course, our old friend quartz, depending on how much quartz is in the product, you're also having to contend with the quartz alpha beta change at 573C, where it shifts and you get an expansion. And this is showing different products and how they react with temperature and the change in length. And basically your quartz inversion is right here. So this purple product, the castable B along with the castable C, both look like they have elevated quartz in it because they're going through the phase change. Okay, hard brick for walls, and again, these are going to be the inner lining brick typically that'll give you a more robust performance with respect to strength and attack, to give you the hard candy shell on your kiln walls. Some of the things that you can see because you're doing fired clay is you're going to have materials evolving off, whether it be binders, plasticizers, or even just naturally occurring alkalis in the raw materials that are firing. Most of this, and this is even potassium in the case of sawdust, most of this stuff, it's going to want to stick to something, and it's not just going to all try to go out the stack or end up in your bag house. And as it gets into the walls, it's almost like freeze thaw, to where it's going to cause something to go on that will start to expand because it'll continue to build up material. And you can have expansions as high as 20% in the surfaces. So again, when you're going through and looking at, if you ever have to work on your tunnel kiln or even periodic kilns, and there's gaps in the walls from the original supplier or the previous person that rebuilt it, chances are there's a reason that that's there. And it seems odd to have these huge overlap gaps, but again, you got to think about it. When you heat this up, all those typically grow together and it'll turn into one solid wall. If you don't leave enough room, again, you'll get bulging. If you leave too much room, you'll get some heat loss through it. So it takes a lot of thinking and discussions and calculations to figure out, how do we actually get this that gives us the best chance that everything's going to knit together. At the same time, you also have to think long term. You could be, whatever you're firing in it can also impact how this stuff's going to perform. When you do this and you start getting these materials depositing, you're also changing the R factor of your wall too, because you're changing the chemistry of it. IFBs, sodium and potassium, generally cause the surface expansion, thermal ceramics type, which can result in sheet spalling. Again, that's where the denser brick typically help you because they have less porosity in it, so you get less infiltration, but it doesn't mean it's not going to happen. Fire brick is typically much more susceptible to it. Key points, all of the deck block are semi-cordierite compositions typically. All contain quartz and cristobalite, so you have to think about the quartz inversion, and can lead to cracking, called dunting. Some plants use unfired deck block. It's a quarter-8 castable, and you do have to be careful on temperature limits and load-bearing capacities, and especially with mixing it, which you'll see a little bit later. Hard brick include typically 60% alumina and Super Duty clay, but again, you have to consider where you're using it. It also helps to not only talk to the manufacturer of the product that you're using, but call other manufacturers if you can stand to spend about 15-30 minutes time listening to their sale pitch as to why their product is so much better than the other guys. But a lot of times you can glean information that could be an issue, because that's what they're going to present to you as to why you need to go with their product instead of the other guy's product. But then it gives you things to think about to say, oh, well, hey, we need to look at that and look at the current product. The one you're getting may still be perfectly fine for it, but you can usually get food for thought out of them. Castables. Castables are designed to cast into shapes and install as linings. When used as linings for process vessels, castables are sometimes called monoliths because they're monolithic. There's no grout joints or anything to put them together. Castables are composed of a cement binder, usually calcium aluminate cement, and aggregate filler. The particle size distributions of the materials are carefully controlled so that you get the right flow and the right density and the right thermal characteristics. The aggregate phase can be mullite, alumina, cordierite, spinel, magnesia, or some combination. And again, it's acting as a filler, and it's just like concrete, to where you're putting something in there that you're gluing all the particles together, but you want to have it to where it has a good balance so it flows and then gives you the strength you want. Castables are usually classified by the cement content primarily, primary aggregate and intended forming. Cement content, you'll see that typically conventional is around 2.5%, somewhere in that range, or greater than 2.5%. Low cement contents are 2.5 to 1, ultra low 1 to 0.2, and cement free or less than 0.2% cement. And again, typically these are going into applications where the temperature is going to be more aggressive on them, so that they'll lower the cement content and shift more to like an alumina aggregate in it. Aggregate type will also be specified, and then what the forming methods should be used when working with it, and that's whether it's vibration casting or self-flowing. Looking at a data sheet, again, you just have to read through it and understand that you're looking at what temperature you're intending to use it for and what the sheet's saying that it's used for. Looking at the chemistry, because again, depending on the percent alumina, it'll give you kind of an idea of what temperature range this is going to be used for. It has maximum service temperature. One of the other important things on castable to keep an eye on, how long you can store the stuff, because this is a hydration reaction. So if you have a bag that's sitting in your warehouse that's 2 years old, you may not want to use it unless you've had desiccant packed around it and basically kept it in a vacuum environment or something, because moisture will eventually make it in the bag and it'll start degrading the strength, and it may act like it's going to cast well, but your strength is probably going to be considerably less than what it's advertised. So
Isn't there something you can add to it? There's
nothing that I know of. And you even have to be careful too on some of them. Again, understand the product you're using. There are some out there that you can sweeten when using it, and there are some that you do not want to add water to at all. That will come in a pre-mixed can. A lot of times when you pop the cover on it, it'll have like almost like a black oily film on top of it, and you want to just get that stuff mixed back in on mortars as well for going through on the pre-mixed stuff. But again, the guys that are selling it to you, you would hope that they've done their due diligence and research, and they're giving you good information as to how to use that they've tested to say, okay, if you put water in it or you try putting an additive in it, you could greatly impact what the properties, the performance properties of the material are. So if there's any question, talk to the manufacturer and say, is there anything that we can put into? But typically it's a hydration reaction, so just like cement, it has to be cracked at high temperatures to get it reactive again. You're trying to break chemical bonds and get it to where it's ready to react again. And usually it's much more expensive to do that than just go out and buy another bag of it. And then again, the permanent linear change, most of the stuff is laid out to where you can look at it, and just from reading the headers you get an idea of what it's telling you, what the temperature, and looking at the heat flow through the walls, what the strength of it is, and again, read the whole thing and understand what you're looking at. If you have any questions, you can call us at the center, or again, better yet, call the manufacturer, and their guys will be more than happy to talk to you on the phone and explain to you why theirs is the best. Castables are sensitive. Water quality, to where if you've got stuff in your pipes and it ends up in, you could be affecting, depending on if you're close to the coast and you have salts that are elevated in the water, then you can end up with issues. Ambient temperatures at which it's cast, cement type, the duty rating of it, the age of the material, the water quantity that you're putting in it, the amount of vibration you're putting in it to get the castable to densify and float bubbles out, curing temperature, and then placement against porous materials, because what's it going to do if you pour it up next to a porous material?
Okay.
It's going to suck the water right out of it, that the water's there to cause the hydration reaction. You suck the water out, it's not going to react. So it's all things you should think about. Thermal expansion comparison. This is looking at, again, different products, unfired deck block, traditional deck block, castables. And there's a reason why when you go out and price a material out that there's a difference in cost, because chances are it's going to perform differently because it was processed differently. And this is giving you some ideas of, as you go up in temperature with these products, to see how very different the change in size is. And again, that's something to understand, that if you're trying to replace a product with another product, things to think about. Castable problems. The castable did not set properly. So this is something that probably may behoove you to even print out and keep copies out for wherever you do the rebuilds on your cars, and or whoever works on the kilns, to not only review before working on it, but if you have a problem. Usually it's better to work on it before so that you don't have the problem, but just stuff to read through and keep in mind as you're going through, to where the water quality, high temperature, casting, old cement freeze thaw, as placed castable density is too low, too much water, not enough vibration. The castable is lumpy. The castable exhibits cracking. So these are giving you all things that you can look at if you start running into these situations. And again, reading it beforehand so that you go, okay, I want to make sure that I get the correct amount of water in here. I want to make sure to get it thoroughly mixed. And when I place it, I'm placing it correctly. Key points: castables are convenient, but you must know how to mix it and place them properly. If the castable is easy to get out of the paddle mixer, the guys have probably added too much water to it. Castables must be prevented from freeze thawing as well, because again, they've got water in it. You go ahead and put it in place, and overnight that thing freezes. You've just put a whole lot of stress and probably induced cracks in it, which will grow once you start heating it up. These for insulated fire brick. can be made out of sawdust burnout process to create the porosity in the refractories. Have a duty rating based on a 24-hour shrinkage criteria, and this is just giving some examples that thermal ceramics may expand slightly in a sawdust-fired kiln, and RHIs typically may shrink in a sawdust. And again, it's because of the process that was used when they were making the insulated brick. For mortars, for Sarset, contains sodium silicate or water glass. This is an eye burn hazard, so again, read the instructions and follow them from a safety standpoint. And there you go. Usually has a dark oily liquid on top. When you're open, you must stir all of that back in, because that's what's giving the performance of the mortar, making it, turning it into a paste so that you can use it properly. You cannot dilute this, because that oily paste is typically not water-based, and if you put water in it, you're going to cause issues with the strength. You can use after it is frozen, but you need to defrost it and remix it, because when you freeze it, it's going to want to separate things. Ceramic fiber. Sold in blanket board and modules. Has a duty rating, but exhibits shrinkage in service typically. Tends to devitrify in service. Has been studied for health effects, so if you are going to use it, it's always a good idea to wear protection when around it. And you can run into some interesting events such as this with it. It has advantages too, to where doing temporary, we have one of our periodic kilns is all fiber lined, and if it starts forming a crack, you just grab more fiber and just tuck it in and go to work. Just make sure you use the right duty rating on the fiber. You don't put a 1400 degree fiber in a 2000 degree kiln, because that'll give you a whole new surprise when it turns to glass and starts melting everything around it. And finally, the roof isn't supposed to be down here, it's supposed to be up here. That there will be issues. Hopefully you don't ever run into anything as big as this, but there will be issues, and the big thing is just go back to your experience, your knowledge, and think about what is going on in the kiln, because if you're heating it up, it's expanding, contracting, and doing all sorts of fun stuff, and chemistry-wise, what's going on in it too, to where your kiln, when you go in and look at the brick in your kiln, they look different than when you put it in. If it was just heat, chances are they would look the same, but there's all sorts of other chemistries that are going on that you have to think about when you're doing repairs or change-outs in kiln. Any questions? Knowledge level go up just a little bit?
An extrusion, like say I was going to get block for kiln cards or whatever, is there any appreciable difference between doing an extruded method versus the press method?
There's going to be a difference, but which one is better for that application, it's hard to say. In that, again, you can have one supplier who shouldn't be extruding but does, or it just depends on what pressure it was pressed under, what the material is. Usually going through and looking at the spec sheets, again, reading all the way through it, and just thinking about what you're reading when you're looking at the numbers for how much does it grow, how much does it shrink on cycling, and what the use temperature is, and how am I going to use it, and what is this brick going to see the entire time it goes through my process, will give you a better feel for it. And the big thing, again, I can't stress enough, that I always look at, because I've seen problems in my experience, is expansion. And that there are so many instances that I've witnessed of where expansion was not taken into account, and how many problems. It usually doesn't scream at you the first one, or I'm thinking more periodic kilns, the one or 5 runs in, but when you get 10, 12, 20 runs in, that's when you usually have little pieces start coming off the corners, and just things start moving that shouldn't move. Or if somebody really doesn't know what they're doing, they put the car in, fire it off, and you can't get the car back out because everything is grown into the walls and dragging. And now I'm not only going to lose my car deck, but all the product that's sitting on the car deck as well. And most the processes that I've been involved with, I started off in the brick industry, and then I moved out in the world into other industries, and most of the other ones I've been involved with, when you lose a car worth of wear, no offense, but the investments that are in that product are much greater than a carload of brick from just the financial investment that you have in it. But that doesn't say that you have your tunnel kiln going and all of a sudden you're in the middle of your hot zone and your car starts to drag and all of a sudden it sticks and you can't push it through. That is a huge problem. So
somebody just gets fired. It's not really
except for the guys that have to go in there and dig it out. And
well, I mean, you're fired, so you don't have to worry about it. You know.
Oh, okay. That's one way to look at it. But yeah, it's something that again I typically promote communication.
On your castable mix, you said if it comes out of the mixer too easy, it's usually too wet.
That's
Is
typically
there like a rule of thumb, maybe like mashed potatoes, or how do you want it?
Manufacturer's recommendation. Yeah, and if there's a question of it's like, should it be that runny? Take a little bit of it, put it in a cup, and put the correct amount in, and just sit there and stir it up and go, okay, what does that look like compared to that? Do we both have chicken soup, or do I have peanut butter and they have chicken soup, and then I know, something's off. Okay. Yeah, it's again just doing some simple math. Stick it in a cup, hand mix it, and it should let you know whether that's. Exactly.
In other words, a 12-inch column of that, it'll slump X inches.
That's the same way you do concrete. Yeah. Yeah, but if you don't have a slump cone, one of the quick, and you might even use that as a precursor, is take some of it, put it in a cup, mix it up with the prescribed water, and just see what it looks like, and show it to your guys and say, okay, this is what we should end up with if we put the correct water in. Now again, it's usually a pain. I've run into the same thing. I'm laying brick at my house right now, building a fire pit, and just for the volume that I want, I'm mixing all the mortar in my mixer, but getting that stuff out, it does what it's supposed to. It sticks, but it's just you gotta mix it right.